Hey, welcome back to Fan Mama Physics. In this video, we are going to show you an example of an experiment or experiments that were able to confirm the de Broglie's hypothesis. Not confirm, but just to show support. So, de Broglie came up with the idea that if a wave is able to act like a particle, why can't a particle act as a wave? So he came up with his hypothesis in which the wavelength of a particle is dependent on its momentum, so displaying wave-like properties. So the experiment to show support for that was an electron diffraction experiment. So if we take these electrons and we give them some kinetic energy, we accelerate it, we get it to this electron with a certain amount of momentum, should display wave-like properties, and we find that in which this electron diffracts when it is incident on, say, these small slits. And what we use to model that would be, say, an array of atoms, so that the electron has to kind of pass through a sheet of atoms, so that the spacing between these atoms to some degree represents the space, the slit size. So after doing some experiments, they were able to show that the relationships that we use for waves for diffraction is similar to that of that the experiment shows for, say, an electron. So highly supporting that of supports de Broglie's hypothesis. And an experiment here, for example, Davison and Germer, is that these electrons here were accelerated. It hits these nickel targets, in which the nickel target has, say, an array of atoms in which it much resembles that of a diffraction grating experiment, and in which the angles of the scattering was measured, and it goes along with support for the diffraction grating equation that we've learned in topic 9. So let's do an example, but I am aware that imagine, hopefully you've done topic 9, but let's say if you haven't, a little bit of what a diffraction grating experiment looks like is, imagine you have, say, a bunch of slits, okay? And in our case, the spacing between our atoms to some degree for nickel is going to resemble that. So, unlike our topic 4, when we talk about a single slit or a double slit, diffraction grating, imagine there's multiple slits, a whole slew of slits, so that when you have an incident light, you get a diffraction pattern in which the pattern kind of looks like these sharp peaks that appear periodically on, say, a screen. So then, similarly, you might have, say, a central maximum, and then the first maximum, etc., in which the D here is the spacing. Okay, the angle here is just the angle between the center versus whatever the maxima, the next maxima, wherever you want. And then the n value here is the number of wavelengths, or we're talking about which order. So that's talking about the path difference. So if, let's take a look at how this can be applied in this experiment. So this, in his experiment, the electrons were accelerated through a potential difference of 54 volts. The spacing of these planes of nickel is this number here. So essentially we're going to use that for the slit size, the spacing of the slits. Sorry, that's a spacing. If the experiment measured at a first maxima n at an angle of 54 degrees, if that's the case, show that the experiment shows support of de Broglie's hypothesis. So essentially what we want to do is we want to show that based off of the results of this experiment, the equivalent wavelength of light hitting these structures is of some wavelength. And this wavelength matches exactly the de Broglie wavelength of these electrons that are going at a certain speed, which we will find from this accelerating potential difference. So we're going to try to find a match here. And if the two wavelengths match, then we can show that this experiment supports the de Broglie's hypothesis. So let's begin with the diffraction experiment. using the diffraction experiment, if we rearrange this for wavelength, we are going to get d sine theta over n, in which d is a spacing 0.215 nanometers, so times 10 to the power -9 meters. Sine theta, which is 54 degrees, over n, which is the order here. So n is equal to 1. And after we put this into our calculator, we're going to get 1.739. So this is roughly 1.7 times 10 to the power of -10 meters for the wavelength. So now let's go ahead and use the accelerating voltage to find out the equivalent, the de Broglie wavelength of these electrons. In the previous video, we're able to show that the wavelength is related to the accelerating voltage in this following manner. Okay, so if you are not aware of this one, maybe check out a previous video, but essentially here, this is this here, EV, electron times the accelerating voltage, this gives you the kinetic energy. Kinetic energy and the momentum are related, in which the momentum is going to depend on 2m times the kinetic energy, in which the kinetic energy is just EV. Okay, so after we substitute in the Planck's constant and the rest of these values to the mass of the electron, the elementary charge, and accelerating voltage of 54 volts, here is kind of what it looks like, and we get 1.67, which is roughly 1.7, and of course this is all very rough, -10 meters. So we show that these wavelengths are the wavelength that we would expect of a light equivalent incident on the sample is as such, which then matches the Broglie wavelength of the electrons that are incident, meaning that it is very, it shows strong support in which matter can also behave as waves as well. Okay, so that is the Davidson-Germer experiment. Okay. So, next up in the next video, we are going to show how, using the electron diffraction experiment, we are able to use that to help us find, or to help us measure the, as close as possible, the size of a nucleus, which Rutherford could not do. Okay, so stay tuned for the next video. I thank you for watching this one, and Fan Mama Physics signing out!